Good day, everyone. Thank you so much for joining us today for this lovely session on using deep learning for flood extent mapping using Sentinel-1. Some of you may already be aware, this is something that we introduced earlier in the year, and you will see as I go through the slides and introduce some of the details that this is actually quite familiar, and it's just something I've been working on and improving, and now we're ready to share for everyone to be able to use. So thank you so much. For those who are in the room right now, if you have any questions at any point, please put up your hand. I think you'd be able to unmute and ask any questions that you have. So just to remind us all that Digital Earth Africa is an organization that is empowering countries across Africa with Earth observation data to enable climate adaptation and mitigation, greater food security, and more sustainable development. And the workflow that I will be presenting today is something that will showcase this exact thing around enabling climate adaptation and mitigation. And of course, everything that we do at Digital Earth Africa is open and freely available to anyone, including for commercial use. And we have optimized not only Earth observation data, but also workflows that we also make available through various interfaces, including a free online learning platform, a help desk, and an extensive library of tools and workflows that we have readily available to you, addressing a number of sustainable development goals. I won't go into too much details on that because I think we're already quite aware in terms of what is available within the Digital Earth Africa platform. So this work that I'm presenting today comes from this great initiative, the Thorough Big Data Africa School, which we had earlier in the year in March, where students were being introduced to using digital Earth observation data through the Digital Earth Africa platform for the most part. And one of the projects that was included in that was on mapping flood extent. And you see that there are other projects that were also there, including crop mapping, mapping and monitoring urban development, as well as peatland and mangroves. But the one that we're focusing on is on mapping flood extent. Earlier in the year, we had a presentation where the team, Aqua 6, that was part of this group working on flood mapping, gave an introduction to what they were doing. First of all, going through a notebook that we have already in the Digital Earth Africa platform for flood mapping, and what we had tried as an attempt to use deep learning for this exact same exercise. So today I will be taking you through that. And this is because floods are amongst the most frequent and damaging natural disasters that are affecting lives, infrastructure, and ecosystems. And we need timely and accurate flood extent maps that we can use to support disaster response, recovery planning, as well as long-term risk reduction. And traditional methods which use optical imagery, such as Landsat and Sentinel-2, are often limited due to cloud cover during these flood events. And synthetic aperture radar SAR enables us to monitor through these clouds and also through the night. Another thing to point out is, although we have showcased an example that we used SAR 4, Sentinel-1 for, we used a threshold approach where we just look at the radar backscatter, threshold it into water and non-water, and then classify areas that we consider to be flooded or new water that is introduced that constitutes flooding. But that in itself is not enough, because these threshold-based approaches can struggle with when you have mixed pixels, where you have land and water conditions, and as well as regional variability. So this deep learning methodology, we're hoping, will be a little bit more robust and a little bit more automated in terms of using SAR imagery for flood mapping. The data that we are using is not it's a data set called SEN1+11. And this is a carefully constructed data set that is designed to train and evaluate deep learning models for flood detection using Sentinel-1. And it is generated by a company called Cloud to Street, which is a public benefit corporation. And this data is widely used for both research and practical applications. So the data that we're using covers real flood events across the globe, as you can see on the screen there. It's collected over 15 countries, spanning different continents. We have the US, we have Paraguay in South America, we have Spain in Europe, and in Africa we have Ghana, Nigeria, and Somalia. And we also have Pakistan, India, Sri Lanka, and Mekong. So we can see there's regional variability, and it includes 4,831 image chips, which span about 120,000 square kilometers. And these are sampled to represent all 14 biomes and 357 ecoregions, so that our model, when we train it using this data, we can generalize to diverse environments and geographic regions. Out of those 4,831 total chips, most of them, which is about 4,370, were automatically labeled using simple remote sensing methods. So these are what they consider weak labels. So they cannot be used for they can be used for pre-training or weak supervised approaches, but they're not the main focus here. Our main focus is to use the high quality portion of the data set, which is the 446 hand labeled chips that we have. And these are carefully annotated and are actually used for training, validation, and testing in standardized or standard supervised workflows like the one that we're going to showcase in this case. And one key advantage, which I already mentioned, is that this SEN1+11, it uses Sentinel-1 SAR imagery, which can penetrate cloud, which makes it perfect for monitoring flood, even during stormy weather when optical imagery would be obstructed by cloud cover. And I already mentioned that this data set includes some various land covers, from urban to rural, agriculture, forested regions, and this diversity makes it suitable for training models that can generalize across different environments, which is really important. As in Digital Earth Africa, we aim to create workflows that are easily applicable in different parts of the continent. So yeah, that is the SEN1+11 dataset that we are using. So I'll first take you through what the training workflow looks like, and then actually open that notebook for us to actually see. So the training workflow was developed by the SEN1+11 team. And this is a notebook that they call Train. I will show you how to access it, because it's important that if you want to retrain the model that we provide with your own parameters or any other changes, you would be able to do that. But I'll get into that a little bit later. But in essence, we're using that SEN1+11 data to train, validate, and test our model, which is a fully convolutional neural network, which is optimized for pixel level classification. So instead of classifying images as a whole, they analyze each pixel individually and determine whether it's flooded or not. So that's how that works. And unlike traditional CNNs, these FCNNs rely solely on convolutional layers. So this allows them to preserve that spatial resolution of the input imagery, which is crucial when you're detecting flood boundaries. And the FCNNs automatically learn complex spatial features from the data, such as flood boundaries, water patterns, changes in land cover, and this enables them to detect flood spread across a variety of terrains. And by processing entire images at once, you're more able or more efficiently able to map large-scale flooding, allowing for quick and accurate flood detection. So on this slide, you see a set of points. I've just summarized how it works. We start by preparing the data. You'll see this when I go through the notebook, the data set preparation, and this includes loading the training and testing, training, validation, and testing splits, which they provide to us as CSVs. So they almost like you put the names of the files that you want to use for training in one CSV, what you want to use for validation in one CSV, and what you want to use for testing in another CSV as links that you can then refer to or call upon when you do your training. And we define a custom PyTorch data set to read the images and the labels and apply any data augmentations like cropping, flipping, and normalization. And these augmentations help the model generalize better. And I said the model we're using is an FCNN with a ResNet 50 backbone. So it's designed for pixel level segmentation. It takes two bands from the Sentinel images, so the VV and the VH, and produces a binary output of flood versus permanent water. And during the training and validation, we use a weighted loss to handle class imbalance, and Adam W optimizer and a learning rate scheduler. We track matrices such as loss, accuracy, intersection over union, just to monitor the performance as the model continues to learn. And of course, you're also able to test this on an unseen data set. So that other CSV that lists everything that you want to use for testing, you use that data to then test how well your workflow is, or your trained model is able to work on unseen data. And when you're doing your training and validation, this graph that you see on this side is something that you're going to see. And this is how you're keeping track of your training as you're going and whether or not you need to stop or you need to continue. But I'll explain that in a little bit. So the original code iterates is said to iterate 1,000 times, but that's just the upper bound. It's not saying you have to run this model until it gets to these 1,000 iterations. So you can see that for my model, I stopped at 250 because after a while, we see that the model performance is not necessarily improving, and actually we're not going to get any more valuable information. And that's why when you have this graph, you'll be able to make these decisions. Let me just take a step back and explain. So this is what the training and the validation notebook that I'm going to show. So this is what you will see almost in the last cell, where you've set up your data, you've loaded it in, you've set up your loops to do the validation, to do the training, to do the testing, and now you're actually feeding the data through to do that for the model to learn. And the training we're using, once again, Sen1 plus 11, and you have the training configuration. You see mine is set to 250, and what that means is you repeat the network sees the data sets 10 times over 250 iteration. So in total, it's about 2,500 times. Like I said, the original data, the original notebook says 1,000, but that's entirely up to you if you want to change that, as I did. And as the model was learning, we were tracking loss, which is the prediction error. So we expect that training loss is steadily decreasing as we do this. And the training loss you'll see here is the blue line at the bottom. It starts off at about just over 0.5 or 50%, and it keeps reducing. So that is expected for that to happen. But we also see that the validation loss will initially increase. So the validation loss is this orange line. Let me see if I can put on maybe a pointer. I'm not sure, but is this orange line right there. I will just erase it so we don't get confused. That orange line is the validation loss. It will initially reduce, but when it starts rising, it suggests that our model is possibly starting to overfit. And in that case, we can make the decision to stop training early or apply stronger data augmentation. So these are decisions that you can make. We're also tracking accuracy, which shows us the proportion of correctly predicted pixels. And this should increase for both the training and the validation. So it's those two lines at the top, the orange and the red, the orange being the training accuracy, and the red being the validation accuracy. If we see large gaps between them, as we start to see in the tail end of the graph, we can expect this can also be pointing out the overfitting. The area over intersection, that evaluates the overlap between the predicted and the true flood masks. And ideally, both of these should improve over time. So we can see this on the graph on the right, that these matrices are evolving as the iterations go on, as the model continues to learn the data. And for the most part, it indicates that the model is learning effectively and it is generalizing well. But an important thing is we save checkpoints, and we do that every time the validation IOU, intersection over union, increases. So the last model we'll always save will be the one with the best validation intersection over union, because this is the one that fit, or the model that generalized to unseen data the best. So as much as I've run it to 250, the model that I'm actually using was at about 172 or something along there. So it doesn't mean that the last where I stop would be the model that I use. It would be the best model, not necessarily, as we can see in that graph. So that's something to bear in mind if you are going to train your own model. But like I said, as Digital Earth Africa, or as the person who created this notebook that I'm going to share later on, you don't have to retrain the model if you're happy with how the model is performing. But if you are not, you are more than welcome to then go fine-tune the hyperparameters of this training notebook that the Sun 1 Floods 11 team gives us, so that you can improve the model performance and generalization over your area of interest. So that's merely a choice. So when I test on unseen data, we see that there's multiple things that we could pay attention to. The two plots on the left, I'm not sure if this appears as a right or left to you, but on my left, we see that based on the Sentinel-1 input that we have and the ground truth mask. I just realized I forgot to rename those. But the ground truth mask, which is what was given to us as part of the testing data, our model was able to predict pretty well to those, to what we see on the imagery, as well as what the labeled ground truth mask tells us. Just in case, because I haven't explained this, let me just say, when we look at radar backscatter, water generally appears dark. So these dark elements that we see, that would be the water. So that's why I'm saying you're able to see where the water is. But we also see examples where what we're predicting aligns pretty well with the raw imagery. So when you look at these ones on the right, but what was given to us as the hand labeled data doesn't exactly correlate with that. And that's what is probably affecting our testing accuracy and it being just only 93%. I mean, 93% is still good, a good accuracy, but we need to bear in mind that some of this label data is inconsistent. This might be human error or a naming error or anything in the data set. And this data set is actually quite old, from 4 years ago, the last time it was updated. I've recently seen an updated version of the data. So I want to see if we can replace this older version with the newer version and if that would ultimately improve our model performance. But in any case, I think with a test accuracy of 93%, where we're looking at the proportion of pixels that are correctly classified as flooded or non-flooded, it's giving a pretty good indication that the model is working well. And this intersection over union of 0.51, which is evaluating the overlap between predicted and labeled flood areas, accounting for both false positives and false negatives. It is lower than the accuracy, of course, but it is expected in the data sets, as I've already explained, it's imperfect or is inconsistent in terms of the labeling, the blue sections. So that is to be expected. But the main takeaway is that the model seems to be working pretty well. And that's something we can work with. So when we do the testing, this is supposed to be, this slide should have been before, so I can show you that this is what we're expecting. We have the raw imagery, we have the hand label data, and the prediction to see how it compares. So this was just a mistake on my end, but I think I've already explained that. And now I will then do a demonstration, but before I go on to the demonstration, I will allow, if you have any questions before I move on to opening the notebooks and showcasing those. If you have any, please feel free to put your hand up or type them in the chat and let me know. Any questions? Yes, Ramson.
All right. Thank you very much for the opportunity. I just want you to elaborate on the intersection of the union, the IOU, a bit for us. Thank you.
So I'm sorry, I am really struggling to hear you. You sound very far.
Okay, I'm just typing.
Hello? Ramson?
Hello. I kept it in the chat. If you can see the chat.
Oh, okay. Sorry, I have, where's my?
Ramson is calling from Ghana. He's a very big champion.
That's great. Oh, you're asking for an explanation of the IOU? Okay. So the three main things that we're tracking, we spoke about loss, which is prediction error. And we talk about accuracy, which is the proportion of accurate or correctly predicted pixels. And the IOU is evaluating the overlap between the predicted and the flood mask. So these are the predicted. Let me just go to that. I don't know if you can see my cursor. Please just let me know if you can see my cursor. But it's the overlap between this, the blue part, which is what we are given as part of our training, validation, and testing data, and the predicted. And I was explaining that it is expected that it would be a bit lower when we see that we have instances like this in our data that we were given. If the data that were given does not reflect what the raw imagery is reflecting, because it's quite unclear to me how this is the flooding when the image itself does not showcase this pattern. But we're able to capture what is on the image, as you can see in the red, the CNN prediction. But the hand label data did not reflect that. So when we do that overlap, that's what we're looking at as with the IOU. Am I saying that right? Yeah. So that overlap is affected by these kind of issues where the handheld ground truth, hand labeled data that we're supposed, almost like the valid, the ground truth data that we're supposed to match is not a true reflections of what is on the ground. And we see that because the raw imagery does not showcase those patterns. And that's where it suffers.
Okay, thank you. Thank you very
Okay,
much.
great. Any more questions? All right, I will stop this and go to, I'll first go through the Send2 flood repository. What I'll do is I'll also put this in the chat for everyone. I think you'll get the notebook, it's the presentation as well, but just for everyone to have. This is the repository that we're following, and they explain what the data is, how you can access it in various ways. I'm not sure if you can still see my screen, or are you seeing the presentation that I just moved away from? Yes, HP has a question.
Sorry, this is Cynthia from Ghana.
Hi,
Sorry
Cynthia.
for the name. Okay. Please, I was asking about the results that you had. Is there any evaluation, something to evaluate whether what we had from the test, the percentage that we had, something to evaluate?
To evaluate from the test how well it did.
Yes, please. Like the 0.93 that we had from the slides that you showed.
Yes. Yeah, so that is the accuracy that tells us the percentage of how well our prediction that we did using the model that we trained matched with the hand labeled data. So that is the accuracy assessment. Were you asking for something else?
Okay. Something dropped in my mind that maybe we had this is our test, the results that we had at 0.93. Okay, what is like we wanted to make some evaluation to show that okay, the test that we had is the actual results that we are getting from our training data sets.
Yes, so it is. So how the data is working or currently structured, there's three, the data has been divided into three. You get the training and the validation data, so what that you put in for the model to learn. And after that, you have an unseen set that you then apply that trained model, that trained and validated model to then get that level of, so it can tell you on this data that it's never seen before, what is the accuracy? And it's saying it's about 93%. And as I've also showcased with some of the figures on the screen, this accuracy is also being affected by the fact that some of the data that is given to us, the blue, let me share my screen again. So this blue, okay, what is it sharing? Okay, so the blue, that part right there is the blue is the hand label data that comes with the raw Sentinel imagery in the test set. And the idea is the hand label data is like almost like digitized flood extent corresponding to that raw Sentinel-1 image. And the red is what we are predicting. So when we do an overlap between the hand labeled and what we predicted, it's obviously not going to be correct, because in any case, that hand labeled data is not a true reflectance of what is currently happening in the raw data. So that is something that is contributing to a slightly lower test accuracy, but I think it's still pretty good.
Thank you.
Okay, so let me share.
Please, will you be sharing the slides too?
Yes, we will share the slides. But before I go on, like I said, you don't have to train a model. You can just use the one that we give you that I've already trained. And I'll explain to you why you probably don't want to train a model in a little bit. And you'll understand that unless it's really necessary, you probably don't want to go through the process of training the model yourself. You'd rather want to go through the notebook, almost like the application notebook, to just do the analysis. But if you do want to, all that information to train the model comes from this repository, which I also put in the chat, the Sen1 Flood 11 repository. And that training notebook is this notebook. And you'll see that this notebook is set up to work in Google Colab. I don't know if you're aware of Google Colab, but it's a free computing environment that you can use from Google. You actually just need a Google account and you'll be able to, you don't really need much. But the issue with that is this code to train relies on GPU. It relies on, basically in simple terms, strong or fast, some serious processing. And you don't have that freely within that Google Colab space. You might have to buy credit. You do get some, but it's only for a limited amount. So maybe you'd have it for like 4 hours. So if you are going to train a model and that model is going to take 8 hours to train and learn, you won't be able to do on the free compute that Google gives you, because the unlimited one is CPU, not GPU. So that's the first thing that you need to bear in mind, that unless you do have these credits and maybe you want to also do it elsewhere, not in Google Colab is just a lot easier. You just sort of open the script and it's written to run there. So there's not much you have to do for it to run. So that's the one thing that I think you should bear in mind if you want to retrain the model. If after applying the one that we give, that we've trained, you feel, oh, I'm not quite happy with the result, and I want to tune the parameters and then apply a new model. But you can do that, and this is the code within that Sen1 Floods 11 notebook. You'll see everything is set up. Downloading the raw data for the training, testing, and validation, how to load it, defining the network for your FCNN. All of that is already included. The only thing you might have to do is the model ends at training and validation. And what I've added to my version of the notebook is that testing aspect. I didn't come up with it completely because they already have a testing loop that they have defined. They just never use it. So all I did was, after my training and validation, I added an extra cell which applies this testing loop and gives me that accuracy assessment, and also added a plot function to also just plot the corresponding data. So the raw Sentinel-1 image, the label data, and what my model is predicting on the test data. So that's the one thing I've added. But if I'll share that notebook as well, and I'll tell you where you will be able to find it later on. But the idea is, if you want to, this repository is where you can get all the information that you need about the Sen1 Flood 11 model that was trained and used in this particular case. And this is the notebook. As I said, it's exactly the same, but I added that one ends here, but I added loading my best model back in and then visualizing the prediction. So I'll share this notebook as well. You can change anything that you want to get it to work. And the way I was doing it, I was saving everything on my checkpoints onto my Google Drive. And this is where I had a whole bunch of models. But the idea is I've changed the code so that every time the validation UOI increases, it will save that model as your latest model. And this is what this is for me currently. And I'm using this model to then do the classification of for an area of interest. And how I'm doing that is I've written a simple notebook. One thing to bear in mind about this simple notebook that we've written is it's not in the sandbox, which might be kind of different. Sorry, I see people waiting in the waiting room. Let me just admit them. So we are used to, when we work with Digital Earth Africa, at least, working with notebooks that are within the sandbox. But I don't know if you're aware, but in the past few months, we've been trying to also diversify how you can access the data in the Digital Earth Africa Data Cube outside of the sandbox environment, so you're not restricted. And this is one such example. I am using Google Colab to do that. Like I said, it's free. And if you are to use this notebook, you won't need GPU, you'll just use CPU for that, because I've already trained the model. But if you do decide to train the model, that's almost like the weight falls on you to train the model with your own resources. But you don't have to if you don't want to. And the idea is we're just applying that model to an area of interest to see if we can rapidly apply or identify areas of flooding. That's it. I won't try to run this now, but as with all of our notebooks, we start with the background, we explain a little bit. I give links to the Sen1 flood data set, the training workflow, and explain what is happening here, how you are now going to access the Sentinel-1 data that we have on Digital Earth Africa, which is this one here. This data that we have on our platform. If you want to read more about it, you can go in and read that in our catalog, but you're going to be accessing that data. I added that performance monitoring thing as well, figure as well, for you to see how the model performed when it was being trained. But the important thing is for us to be able to access Digital Earth Africa Data Cube outside of the Data Cube, we need some dependencies, and that's why we're starting by installing these dependencies. These are what allow you to then have access to the data, the ODC stack that you can then use to access the data from. And of course, once you have installed those, it also allows you to use these functions that we have outside within the Digital Earth Africa tools outside. So you're able to call those in as well. So this is pretty basic. You dependencies, libraries. You're starting a session, pretty standard. Now you need to configure the data that you're going to load. That is also explained here, and this is what you do. We're getting the data from the stack catalog. So these are the things that you define. We're getting the Sentinel-1 RTC from Digital Earth Africa. So this is something that you need to do to allow you to access your data. And of course, everything from then on is pretty standard. Set an area of interest. For this particular example, I used an area in Garissa County in Kenya, which experienced floods between March and May of 24 in that rainy season. So this is the example that I'm showcasing, but of course it's flexible. You can apply this to anywhere where there is data for your area of interest and your time of interest. So I've put my longitude and latitude. You're quite familiar with how to do this, and obviously creating a buffer and then creating a geo box or a box around that for that to be our area of interest. And this is the date that I've picked. What's really important when you doing this sort of analysis, you need a before and an after. So because we know the rainfall or the flooding happened between March and May, not sure exactly when it started, but between somewhere in March and May, just to be safe, I'm going to pull data from February to the end of May to see if there's imagery available that I can then use for my analysis. So after I've defined that, I search for that data, and we see that it found 10 data sets. That's just, it just searched and found in the stack catalog. It didn't bring it in yet. And this is how you then load it. It's called a stack load function. Within the Digital Earth Africa platform, with the sandbox, you're more familiar with DC load or load ARD. It's the same kind of thing. You want to load these items that you've searched for, and you want these bands, and you have what your CRS, your resolution, for that area of interest. So that's also pretty standard. And you see it comes in as a DOSC array. What I like to do for this kind of analysis is plot the data so I can see if the data has full coverage. Sometimes it might be half an image, and which ones I want to use. So for this particular example, I picked the first image somewhere in the beginning of February. So the 2nd of February is my before, because I'm sure that by this time, there was no rainfall. It's my before image. And for my after image, I chose the 5th or the 8th of May. And I chose this because I was doing some research and I saw that somewhere around the 29th of April, this area was covered by quite a lot of water, but it's unfortunate that I don't have an image that is for that day. So I just picked the closest one after that specific date, which happens to be the 8th of May. And we can even see just from a visual inspection that it appears a little bit darker in this area. So there's a little bit more black, which we associate with water, than there is in the previous images, especially the one that we picked as our pre-flood image. And so this could be our post-flood image. Or more like post-rain event image. So here, now that I've seen and I've selected 1st and the 8th. Turns out I selected this one and not this one. So how you count them is this is 0, this is 1, 2, 3, 4, 5, 6, 7, 8. We count from 0. So 1 is this one on the 14th, and 8th is this one on the 8th of May. So that's what we are defining as our pre and post. And we only leave those in our array because we don't want to be analyzing all this data. We just want the pre and the post, the 2 timestamps. And now we prepare the model. You see, I'm loading the model that I've trained, which I've kept in my checkpoints folder in the Google Drive. When you get this notebook, it will be on a repository. So this that I've commented out will be how your code looks. That's how you'll be able to pull the model that I give from our GitHub repository. But right now I'm pulling it from my my Google Drive. So just bear that in mind. We load that in. And then we run the prediction over time. I just also highlighted a few steps here. You're handling missing data, you're transforming your data to decibels, your radar backscatter to decibels, and also clipping it to the range of -50 to a 1, because that's how the model we've trained, this model from the Sen Floods 11, that's how it accepts the data. So it's not something I've just come up with myself. If you go through this notebook, you'll actually be able to see that process happen where they normalize. See, you will actually see that actually happen within that training process. So that's what's happening there. And then we do our prediction over time. So this is the note, or rather the code that does that. What I've added is, because when we do an automatic classification or prediction, it will create a binary flooded, not flooded, on a 50%. What I've done is I've given the option for you to be able to change that threshold of 50% with this code right here. So where you combine your probabilities, it's not based on the radar backscatter, but the probability of an area being flooded or not flooded. Instead of just going with an automatic 50%, you can use an also threshold to say combine the pre and the post, and then find an area, or find or sort of like a cut point to say this is what properly distinguishes between water and non-water. If you want to go with the automatic one, you can also do that, but that option is also available. And so it will tell you what threshold it's going to use. See, for instance, a 0.31 instead of a 0.5. That's an option. And then you can visualize. So what I did for the visualization, I have the pre and post. The pre-image, I think this is a VV image, VH image. You can have a VV image, doesn't really matter. Just something to use as reference as to what we're looking at. And the post image, we can clearly see on the post that there's a little bit more that's happening around there. So we can expect that there's a little bit more water, and we see that in the pre and the post. But one thing I will say, we also notice that some of this is clearly a river system. And in the pre, we see that this area has water, and suddenly it doesn't have water in the post. This is just how the model is interpreting the data that it's getting. It could be a number of things: the turbidity of the water, the sedimentation that is in the water, the movement of the water after or during this flood event can disturb our backscatter, and it can make it appear as if that water has disappeared. But no harm with that. So what I've then done is I've taken this as our permanent water. Whatever is in the image, that is what we consider our permanent water. And anything that is added in the post, that is then classified as the flooding. So we see that blue there, we're calling that permanent water, and that comes from that pre-image. And the green is what is additional when we look at an evaluation of the post-flood image or the post-rain image. And I've also added like a map that you can go in and visualize, and so you can have a clear, because this one here, you have no context. You need to have context, and that's why I added an interactive map that you can go in and see those changes. Also, another thing you'll notice here, there's also quite a few areas that when you go to the interactive map, you see those are not actually areas of water. Let me see an example. That would be the blue. So for instance, let's just look there. Doesn't seem like there's a water body, but that suggests that this is permanent. This is permanent water. But this is because with the radar backscatter, there's some things that could be misclassified as water because of their spectral signatures are quite similar to what water is. So maybe the soil was damp or wet, or maybe there was a shadow, or just very smooth, bare soil can also do that. So those are some instances where that kind of information can creep into, the analysis. So this is the notebook, and with this notebook, where you will find it, I would put it in there yet, because like I said, I want to try that new data set that I saw earlier. And then, but it will be in this new repository that we have that is called Direct Access. I'm putting that in the chat as well. So this new repository is where we're putting notebooks where things are being done outside of the sandbox, be it on Google Colab, be it on your own computer, be it on SageMaker. All of that is included in here. And if you want to know how to get started, there's a simple Digital Earth Africa loading demonstration notebook that Michael has put in there, which just gives you a brief introduction to how you could access some of the Digital Earth Africa tools, and as well as the data outside of the environment of the sandbox. So this is where this data will be, most likely within the real world examples note folder. It'll be in there. Its model will be in there. And all you have to do is, it'll be something like this. If this would just open, but there will be a little tab on top that says open in Google Colab. And all you have to do is, okay, it's not that one, but it's this one. All you have to do is click on it and it will open in Google Colab. You can run the example that is already there, or you can change your location, change your date, change the extent. And if you want to create your own model, you wouldn't have to download the model from the repository, because that link that I have in there, it will pull it straight from the repository. So it'll look something like this, where if you click on this, open in Google Colab, you see it goes straight directly to Google Colab, opens the notebook, and you're already able to run it as it is. And of course, you can make any changes. So I will be adding that notebook into this folder, as well as the model and my version of the Sen1 Flood 11 one, which I've added those 2 extra cells. They will be in this repository for you to have access to. And any feedback on it is highly, highly appreciated, because there's always room for improvement. And we would be happy to do that based on your feedback. I've been speaking for quite some time, so please, if you have any questions.
Hello,
Yes, Ramson.
please, can you hear me now?
Yes, I can hear you much better.
Okay, thank you. So I'm quite interested in how you define your own threshold. I mean, the probability of water or no water.
Mhm.
Did you consider the backscatter values of maybe what is the backscatter value of water and that of not water? I mean, the surfaces. Is that what place you
No,
considered? Okay.
no. So that is actually something there's a notebook that we've done on that, which is a simple case of mapping flooded areas, where we just say, looking at the backscatter, let's threshold the backscatter. And this is not the case. So this one relies on a probability. So the thresholding is on the probability from the classification of the deep learning model. It's just an option if you don't want to use the default classification and you're like, oh, let me just base it on a threshold of the probabilities, because if you were to plot the probabilities, you would be able to get a nice distinction between what was water and what was not water. So it's just for that. It's not even something you have to use, but if you want to use it, you can. So, it's not off the backscatter. We're not dealing with the backscatter because the model is predicting based on the backscatter. It's just of the probabilities.
Okay, all right. Okay, thank you very much.
But yeah, once you get your hands on this code and you have any questions, please reach out to me. We can improve it. We can work on it. We can make it better and more usable for everyone. All right. Okay, if there are no questions, thank you so much for coming and joining us today. I'll be looking forward to us interacting over this great new thing that we have available. Thank you.
Thank you so
Thank
much
you
for
very
this
much.
great presentation. And also thank you all for joining us. We also have the learning platform, which is having some of these courses, and we'll be adding more courses based on the demand, and also acknowledging one of the participants, Mamo from Addis Ababa University, whom we work together to develop the course on introduction to Diwasa products with EMI. So these live sessions are every week. Today we had the session in English. Next week we'll have the session the same in French. And the other week we'll be having something on water quality, and also acknowledging the partners who made this work possible, Harms Trust and the Australian government, and each one of you. And also the best acknowledgement is the team from Big Data School. We have Osborne who joined us. Also Rebecca is here. A shout out from Rebecca from Ghana, Osborne from Mozambique, Gloria Iona from South Africa, Felipe from Madagascar. And also their mentor Humpo, who was really with them and continues to walk the journey with them. And also grateful for all of you joining us today's live session. This session will be shared with us shortly, including the presentation, and also thanking our presenter, Mpo. Thank you so much, everybody.